Assalamu alaikum everyone. Welcome to another video of O Levels Chemistry at O Levels Pro. So today we are going to discuss a rate of reaction. Rate of reaction means speed of reaction, that how fast or slow a reaction is going. Okay, so there are different factors that affect rate of reaction. We are going to discuss those factors one by one. So repeating again, there are various factors that affect the speed of reaction. We are going to go through all of them one by one. First one is temperature. So, temperature. First, we need to understand what determines the rate of reaction. What determines the speed of reaction? The speed of reaction is determined by number of effective collisions. When molecules collide with each other effectively, successfully, when they collide with each other, they contribute to the speed of the reaction. So, any factor that has an effect on the number of effective collisions is going to have an effect on rate of reaction. So how does temperature impact rate of reaction? So when you're increasing temperature increases rate of reaction. Increasing temperature increases rate of reaction because kinetic energy increases, leading to more effective collisions. So there are 3 marks there. Okay, so if they ask you about the effect of increasing temperature on rate of reaction, and it's a 3-mark question, you will write increasing temperature increases rate of reaction because kinetic energy increases, which leads to more effective collisions, and vice versa. What does vice versa means? That decreasing temperature will decrease rate of reaction because kinetic energy decreases, which leads to less effective collisions. The second factor that affects rate of reaction is pressure. Okay, so increasing pressure increases rate of reaction because molecules come closer, leading to more effective collisions, leading to increase in number of effective collisions or more effective collisions. Same thing, but you always need to write effective collisions. Okay, so then again you get 3 marks, and vice versa. In decreasing pressure will decrease rate of reaction because molecules will move further apart, which leads to less effective collisions. The third factor is concentration of the reactants. So how does concentration work in contributing towards the rate of reaction? So increasing concentration increases rate of reaction because number of molecules increase. Which lead to more effective collisions. Right. So there's another factor, that is fourth one, that is surface area. So if you increase the surface area, I'm writing surface area as SA. So when you increase surface area, you increase rate of reaction because of more effective collisions. Now here one thing needs to be clarified is that if you have, let's say, if you compare powdered something, let's say powdered zinc, maybe comparing powdered zinc with zinc chips, the chips of zinc, not French fries, chips as in pieces of zinc. Okay, so which one of these will have more surface area? Just remember that powdered, the smaller the size of the particle, more surface area will it has. It may not sound correct on first hearing, but let me hear. So hear me out first. Okay. The thing is, let's say if I took 5 gram of powdered zinc and 5 gram of zinc chips, okay, and you place it on a surface, you will see that powdered zinc will obviously occupy more space because it has smaller size, which means more surface area. It occupies more surface. Okay, and as compared to zinc chips. So that's why powdered zinc will dissolve quickly, will react faster because it has more surface area. Or if you want a more commonplace example would be, let's say if you have powdered sugar, which is icing sugar, versus granulated sugar. Okay, we know that icing sugar dissolves faster. Why? Because it is smaller in size. So when something is smaller in size, it increases the surface area. When it increases the surface area, uh, that increases the rate of reaction because of more effective collisions. Okay, the last factor that you must be familiar with is the catalyst. We've already done that. So catalyst increases the rate of reaction. Catalyst increases the rate of reaction by lowering the activation energy. It increases rate of reaction by lowering activation energy. So these are the factors that affect rate of reaction. Now moving on to various ways of measuring rate of reaction. Some of it we have already discussed in the first chapter. Okay, there are two methods of measuring rate of reaction. Method 1 is by collecting gas. Okay, and by basically collecting gas and measuring its volume, and the other one is by measuring loss in mass. Right. So let's discuss that. One of the if you're using method number 1, the apparatus would be something like this. You'll have a conical flask, and at the neck of the conical flask there will be a gas syringe like this. There will be a gas syringe, that is the plunger. Okay, and this will be enclosed. You can have a tap funnel over here. Right. This is going to be enclosed. What happens here? And you need a stopwatch over here as well. So, how does we measure rate of reaction? Let's say if an acid and let's say if HCl and calcium carbonate are reacting. We know that metal carbonates, when react with acids, they release carbon dioxide. So carbon dioxide will be released. When it releases, so it enters into the gas syringe, which is marked. It enters into the gas syringe and starts pushing the plunger. Okay, as soon as the gas starts to be released, or you can say whenever both of these reactants come into contact, we start the stopwatch. Okay, let's say if after 1 minute, 2 centimeter cube of gas was collected. After 2 minutes, 3 centimeter cube of gas was collected. After 4 minutes, 5 centimeter cube of gas was collected. After let's say 6 minutes, they were again 5 centimeter cube of gas collected, and after 8 minutes 5 centimeter cube of gas is collected. These constant values of volume means that no more gas is being released, which is why the plunger is not moving anywhere. That is why it is giving a constant volume value. Okay, now if you plot it on a graph, how would you plot it? Okay, it will be volume of gas and time. Let's say after 1 minute the volume of gas was 2 centimeter cube. After 2 minutes it was 3 centimeter cube. After 4 minutes it was 5 centimeter cube. I'm just writing some random points. Okay, and after 6 minutes it was again 5 centimeter cube, so it will have the same distance on the y-axis. And after 8 minutes it is again 5 centimeter cube. So if we draw the curve here, it will be something like this. As you can see, the curve becomes flat at the end. This flatness means that no more volume of the gas is being collected even though time is passing. It shows that the reaction is complete. Okay, so how do we exactly measure the rate of reaction here? It's simple. You take the volume of gas that is collected, you take the volume of gas that you have collected, okay, and you divide it by the time in which it is collected, and you will get the rate of reaction. So let's say if I increase the rate of reaction here, if I just increase the temperature, the temperature of this curve was T1, let's say. I have to draw another curve whose temperature is T2 and T2 is greater than T1. So what will happen? This curve will move to the left. This curve will move to the left, but it will start and end at the same point, but it will move less towards time and more towards the volume of gas. It will move less towards time and more towards y-axis, because it will be taking lesser time. That's why it is moving lesser towards time. For better understanding, let's say this was 2 minutes. After 2 minutes, according to this curve only collected this much gas, and after 2 minutes the curve in green collected this much gas. So clearly the green curve is a faster curve because it is collecting more gas. Okay, so always remember, whenever there are two curves which are starting and ending at the same point, okay, the left curve, the curve which is going to the left, or the curve that is traveling less towards the x-axis and more towards the y-axis, so please understand that that curve is going to be of the faster reaction. Okay, and starting and ending are the same because all of the factors that we have studied, they only affect the rate of reaction, not the amount of product formed. Amount of product remains the same. That's why the curve ends at the same point. Okay, now let's do the other method by measuring loss in mass. Let's do that. So its apparatus is pretty simple again. It's very simple. You draw a conical flask. You place it on a mass balance. You will place it on a mass balance. Let's say the mass balance shows 50 grams. Okay. I placed soaked cotton on it. Soaked cotton. Okay. So I again added calcium carbonate and HCl into it. Carbon dioxide starts to get released. Now here we are not going to collect the gas. We are letting it go into the atmosphere, and this loss in gas will result in the loss in mass inside this conical flask, and we'll measure this loss in mass over time. Let's plot it. Let's say at 0 minutes. At 0 minutes, the grams were 50. Okay. At 0 minutes, the grams were 50. After 1 minute, the reaction started to happen. Then after 1 minute has passed, the grams reduced to 48 grams. Let's say after 2 minutes, they reduced to 47. After 3 minutes, they reduced to 46. After 4 minutes, they remained at 46. And after 5 minutes, again they remained at 46 grams, obviously. Right? What does this constant value suggest? It means that no more gas is being evolved. That's why the mass stays constant. It shows that the reaction is complete. So before moving on to the graph, I need to tell you why we place soaked cotton here. Soaked cotton is perforated. Gas can pass through it. And the whole point of this experiment is to let the gas through into the surroundings. Let the gas release into the surroundings. But why are we placing this soaked cotton over here? It is to make sure that the release of the gas is delayed a bit, so that you can monitor the rate of reaction. Okay, if you let's leave it open, gas will be immediately released and you won't be able to measure the loss in mass against time. This is just to delay the process, okay, so that you can actually plot it. You can actually see how the rate is changing with time. Okay, so let's plot this diagram. Let's plot this on a graph. So on the y-axis is loss in mass. On the x-axis it is it's going to be time. So at 0 minutes the mass was 50 grams. Okay, after 1 minute the mass reduced to 48. After 2 minutes the mass reduced to 47. After 3 minutes the mass reduced to 46. After 4 minutes mass remained at 46. After 8 minutes the mass remained at 46. What would be the curves look like? Like this. like this. It will be straight. Uh, doesn't look straight, but it is straight like this. Now this flatness shows that the reaction is complete. That the reaction is complete, that the mass is not decreasing any further, which means that all the gas is being released, so the reaction is complete. Okay, now if you increase the temperature here as well, if you increase the temperature, fast fact that this curve is T1 and the curve I'm going to draw now is T2, and T2 is greater than T1. So the faster curve will be drawn to the left so that it travels less towards the x-axis and more towards the y-axis. It will start from the same point and end at the same point, but it will be on the leftist side. It will be on the left side, less towards time and more towards loss in mass. Okay, you can also actually use these curves to gain more clarity. Let's say after 1 minute, according to this curve, this is the loss in mass, and according to this curve, after 1 minute, this is the loss in mass. So clearly the green curve has lost more mass, which means it is faster. Okay, so always remember, whether you're measuring rate of reaction via this method or this method, the curve on the left is going to be the faster curve, and they're going to start at the same point and end at the same point. Okay, as far as these factors are concerned, all of these factors are not going to change the amount of products. Okay, the amount of product can only be changed if you change the amount of reactants. So these factors are not going to have any impact over it. Okay, so that's all from rate of reaction. Now let's do some past paper questions to gain more clarity on the way the questions are asked. So question number 1. The diagram shows the apparatus used to measure the rate of reaction between calcium carbonate and HCl. The mass of the flask and the contents is measured at regular intervals of time. Which graph correctly shows how the mass of the flask and contents change with time? So the mass of the flask is going to decrease, right? So it is going to decrease, and then it is going to decrease, but it will not obviously be 0, because there will be some mass of the liquid here and the mass of B and the mass of the flask itself. So it cannot be 0. So A cannot be the answer, B cannot be the answer, because mass is being reduced to 0. So this cannot be the graph. D cannot be the answer. C seems to be correct because it has flatness to it as well, which shows that the reaction is complete, and this curve has not ended at 0 mass, and it's not possible that the mass becomes 0, because there is the mass of obviously the salt that is formed along with the water. Okay, changing which reaction condition does not affect the rate of this reaction? If limestone reacts with hydrochloric acid, limestone is calcium carbonate. It's a solid, it's a gas, it's a solid, it's a liquid. So obviously pressure is not going to have any impact. Pressure only have impact on gases. Okay, because only gases are compressible. Okay, question number 3. Which change will decrease the activation energy of the reaction? Addition of a catalyst. Catalyst reduces the activation energy of a reaction and increases its rate. The following changes could be made to the conditions in the reaction between zinc and HCl. Which pair of changes will increase rate of reaction? So if you increase the concentration, it is going to increase the rate of reaction. If you increase the particle size of the zinc, it is going to decrease the rate of reaction, because surface area will decrease. If you increase the pressure, pressure does not have any impact, because zinc is a solid, HCl is a liquid. If you increase the temperature, so obviously again rate of reaction would increase. So answer would be 1 and 4. Which statement about catalyst is correct for a typical equilibrium reaction? A catalyst can either be inorganic or organic species. A catalyst does not take part in the chemical reaction. A catalyst only speeds up the forward reaction. A catalyst provides the energy required to start a reaction. So the answer would be A. Catalyst does take part in the reaction. Okay, catalyst speeds up forward as well as backward reaction. And catalyst does not provide the energy required to start a reaction. It lowers the activation energy. Question number 6. This is fun. Now 10 gram of magnesium ribbon reacts with 2 moles per dm cube of dilute HCl, and 5 grams of magnesium powder reacts with excess of 2 mole per dm cube of HCl. Now, magnesium ribbon and magnesium powder. This reaction is going to be slower. Reaction 1 is going to be slower because magnesium powder will lead to faster reaction because it will have it has more surface area. So reaction 2 will be faster. So the curve of the reaction 2 has to be on the left. So B cannot be the answer. C cannot be the answer because reaction 2 has to be on the left. Okay, now left with A and D. Now reaction 1 and 2 cannot end at the same point. Why? Because in reaction 1 10 grams of magnesium is being used, which will release more gas as compared to 5 grams. So reaction 1 should end at a greater height as compared to reaction 2, like in this reaction, and reaction 2 must be faster, must go towards the left. So the answer would be D. Okay, question number 7. Which results show what would happen if the reaction were repeated at a higher temperature? If you repeat the same reaction, that zinc carbonate react with HCl, what would happen? If you increase the temperature, reaction will be faster and volume of carbon dioxide will remain the same. Because temperature does not, any factor that affects rate of reaction does not increase the amount of product. Okay, it only increases the rate of reaction. So don't forget that. Okay, let's do this. This is fun as well. In experiment 1, an excess of finely powdered marble is added to 20 centimeter cube of HCl. In experiment 2, carried under the same conditions of temperature and pressure, an excess of marble chips is added to 20 centimeter cube of the acid. So experiment 1 has finely powdered marble, experiment 2 has marble chips. So obviously experiment 1 is going to be faster. It is going to be faster. And since both are being same amounts are being actually added to the same amounts of the acid and under same conditions of pressure and temperature, so 1 and 2 must end at the same point. So x and y can be 1 and 2. So but you will have to see experiment 1 is faster. Experiment 1 has to be faster, so x is faster. So x will be 1 and y will be 2. Okay. Predict and explain the effect of raising temperature on rate of reaction. Increasing temperature increases rate of reaction. Increasing temperature increases rate of reaction. Because Ke increases, leading to more effective collisions. More effective collisions. Okay. Let's do question number 12. Which alteration to the original experimental condition would produce curve 2? So, how would curve 2 will be produced? Since curve 2 is ending at a higher position as 1, so curve 2 must be made with more amount of reactant. Okay, between 1 and 2 there will be the change in concentration of the reactants. So how would that happen? Lowering the temperature? No. Temperature is a factor that only increases the rate of reaction. Adding some this much H2O2, hydrogen peroxide solution. Hydrogen peroxide is the reactant. If you add some of it, so obviously more gas, more product will be formed, more oxygen will be formed. So that's why it is giving the second curve at a higher position. So the answer would be B. So I hope that you understood these questions. I actually did with you some of the tough questions that come from rate of reaction chapter, and I hope you got the gist of the chapter. Inshallah, I'll be back with another video. We'll be talking about reversible reactions. Until then, take care. Allah Hafiz.